Oh, well, I'm going to do this for another 3 months. Okay, should we start? Or? Okay, so I'm going to get started now. So today's lecture is going to be about applications of the ideas that I discussed last time. That's this duality between color and kinematics. And I'm going to show you how you can use this idea to study the ultraviolet properties of gravity. So with gravity, people make a lot of statements which may or may not be true. And what you need to do is some calculations to see what's true and what's not true. Oh, that's not a good sign. Oh, the screensaver went on. Oops, what'd I do? Oh, I must have hit the... Oh, there's another button there. There's a hidden button. No? Ah, the hell with it. Here. Oh, is it the other way? The other button? Huh, I don't know. No, I don't think so. I don't think it's working. Well, okay, never mind. So, in fact, everything that I'll be talking about today was discovered in n = 4 Super-Yang-Mills theory. And you can take this as another example of why people say n = 4 Super-Yang-Mills theory is the hydrogen atom of the 21st century. You can learn things about gauge theory and about gravity in n = 4 Super-Yang-Mills theory that you can then carry over to other theories. Here, in fact, I'll just be talking about n = 4 Super-Yang-Mills theory, but the same basic ideas can carry over to other theories. Aha. So first, let me just review the previous lecture, just to go over the basic ideas that we're going to be using. So the first thing is there's this duality between color and kinematics. So this would be a tree level. There's, say, a 5-point tree amplitude. We write it in terms of these cubic diagrams, the same ones that you get in phi cube theory. The color factors written here are just the normal ones with FABCs. There's a little tilde is just because I normalize things correctly, other people don't. That's a joke, but anyway. There's the numerator factor. The numerator, I'm writing it here in terms of polarization vectors, just to show you that there's nothing fancy going on. This numerator is just an ordinary numerator. Of course, you really should use better variables, whether it's spinors, momentum twisters, or what have you. And then down here, these are just ordinary Feynman propagators that you can just read off the diagrams. And the statement is that there exists a representation such that for every color Jacobi identity, there's a numerator Jacobi identity. And there is such a representation. Now, as I explained, I'm not telling you how to find this, but if you know the existence of it, then in fact you can find it. Right? The key thing is to know which way you're going. And the reason why this is interesting, probably the primary reason, is that it makes gravity free. Once you've done this for gauge theory, and these numerators satisfy that property, then you get gravity just by taking the color factor and replacing it by the numerator, and that's gravity. And then, of course, there's, say, philosophical things. But this obviously cries out for some kind of a unification of gravity and gauge theory at some very detailed level. We have that the dynamics of the theory, of this gravity theory, is the same as the dynamics, or built out of the same objects as the dynamics of QCDs. Obviously, these theories do not belong separately. They belong unified, maybe like in string theory. And another reason why this is important is there's really been a tremendous advance in planar theory and planar n = 4 Super-Yang-Mills. And you would like to carry the information that we learned from the planar theory. For example, Nima is going to speak about dual conformal invariants. And that's something very powerful in the planar theory. And what this duality does, this duality between color and kinematics, is it allows you to carry information from the planar theory into the non-planar theory. So if we have this duality, we can just look at, let's say, a two-loop diagram here. And this is non-planar contribution. And you see the duality implies that the numerators can be obtained from the planar case. So the information is in here. For example, if you have dual conformal invariants on the planar side, obviously this knows about it because that's an equal sign there.
And every set diagram can be decomposed into diagram elements?
So the claim is this is an unproven claim. It's proven in the cases we've checked it because we've checked it, so it's true. There, you can always, all the information is in the planar. You can always rewrite these non-planar numerators in terms of planar. Now this is at the integrand level. It'd be much better if it was at the integrated level, but it's okay. We can exploit this already. Yeah?
So are these things exactly equal, or is this
equal.
So everything that's in there is
the equal refers to the numerator, not the Feynman propagators. Okay? It's only on the numerators. It's also equal on the color factors. And of course, this is maybe the best part, is now gravity is free. All you need to do is arrange your Yang-Mills so it satisfies these properties, and then immediately you have gravity. So the problem of gravity in perturbation theory is reduced to a problem of Yang-Mills. And actually, here's a nice example of 3 loops. This is the guy I'm going to do on the blackboard. And what you see here is exactly what you see there. I'm just copying the diagrams. These are the diagrams of n equals 4 super Yang-Mills theory. And the way it works is there's a set of Jacobi relations that relate all these diagrams. And then there's a bunch of diagrams I didn't write down because they're 0. I'll explain more about why those things are 0 in n equals 4 super Yang-Mills. But anyway, there's these 12 diagrams, and all the numerators are related to each other. And the relations are powerful enough such that this diagram right in the middle, that's diagram E, we're going to call him the master diagram. If you know that one diagram, you know everything. So that's why I'll be able to do it on the blackboard. I only need to calculate one diagram. And then we're in n equals 4 super Yang-Mills theory, the hydrogen atom of the 21st century. Therefore, I can actually do it on the blackboard. Right? If we had QCD, I'd need an incredibly large blackboard. Okay. And okay, I know the master, and then the Jacobi relations, they tell me everything else. In fact, let's have a look at the Jacobi relations. I was hoping I could put it on the blackboard. See, I started writing it there, but then I decided no one would be able to see it. So, okay, there's the transparency that should have been on the blackboard. Let's look at this one. So in here, I have some canonical, there's some canonical labels. Which one is H? H anyway. Or maybe I should look at another one. But let's say, there's diagram H. This is the Jacobi relation. There's this, and it's got certain ordering of legs. So there's some canonical labeling that I'll explain a little bit later. But you see there's 3 terms. Diagram H is related to diagram G minus diagram I. And that's a Jacobi relation. So it comes in 3s. Then when you look up here, you might see, oh, look, it's only coming in 2s. The 3rd term is missing. But that's because that 3rd term is 0. And I'll explain on the blackboard why that 3rd term is 0. But anyway, this is the complete set of Jacobi relations that I need to solve the problem. There are more Jacobi relations, but they carry no extra information. And in fact, if you look carefully, if you take out your binoculars, then you'll notice that statement that diagram E is the master. So we could start here. Diagram L is in terms of diagram G. Then I go look, where's diagram G? Diagram G is diagram E. I look at, let's say, diagram J. Diagram J is in terms of diagram E. K in terms of F. So then I look at F. F is in terms of E, and so on and so forth. So it's this set of equations then determines the entire amplitude in terms of the one master, which is right there. Diagram E is the master. Everything is determined in terms of that. Okay. This is the thing I'm going to do on the blackboard. I will calculate this. This is okay, there's some story here about n equals 4 super Yang-Mills and duality relations and color and kinematics, but is it really true? So the idea is you check it against a known answer. So we knew the answer in a different representation, so now you use these ideas, and then you solve for these numerators in terms of diagram E, and then you check all the unitarity cuts. Right? So that I'm not going to do on the blackboard. I'll just assert that once you solve the set of duality equations, then you just make sure that, in fact, it is the correct answer by making sure it has the correct unitarity cuts. Okay. Just for amusement, there's 4 loops. So 4 loops, they've got 2 master planars. See, these are planar diagrams. This guy and this guy is planar. And if you know these 2, then you know everybody. In fact, it turns out there's one non-planar guy that can act as the master. These master guys, they're not unique. It's just guys that you need to solve everybody else in terms of. Okay, so let's talk about the ultraviolet properties of gravity. Yeah? You have to solve, it comes from solving the Jacobi equations. So who will be the master? You write down a set of Jacobi equations and solve them, and then you see who's the master. No, it's a little more complicated. It's curious, it's a little more complicated in n equals 4 super Yang-Mills theory, because there's a lot of zeros all over the place. And tracking exactly where the zeros are makes it harder to figure out a priori what it is. Okay, so let's apply it to something. So something good to apply it to is the question of the ultraviolet properties of gravity. So everybody says that gravity is going to be worse behaved in the ultraviolet. I mean, it's just accepted that it's going to diverge, and the argument basically goes like this. Let's compare gauge theory to gravity. If you look at gauge theory, it's got a dimensionless coupling. Gravity has a dimensionful coupling. Therefore, you need extra powers of momentum in the numerator to soak up the dimensions. This integral is more divergent than that one because it has more powers of momentum in the numerator. Right? And that's all there is to it. And you can make it extremely fancy and write very complicated papers about supersymmetry, superspace, this argument, ectoplasm, whatever. But this is the basic argument. The thing is dimensionful coupling, therefore it's non-renormalizable. Now, I think if you've gotten anything out of my lecture and Nima's lecture, it's the fact that there's hidden structures in the amplitude, and one must be cautious about these types of arguments because they're just based on looking at one piece of the amplitude and doing some power counting. Now, we're going to be looking at n equals 8 supergravity, and the reason why we want to look at that theory, to look for what the divergence property is, if you were going to pick any theory of all possible theories and ask which is the one that has the most likely to be finite, this is the one. And the reason is kind of trivial. It's because it's the most supersymmetric. The more symmetry, the more cancellations. That's one of the things supersymmetry does for a living. But the other thing is very important that lines up with the idea that we're really interested in this particular theory is that it has very high technical simplicity. It's the simplest quantum gravity that you could possibly pick if you were going to analyze one. So these 2 ideas line up one on top of the other. So this is the theory we want to look at. Now, let me just make a little disclaimer. So the reason why we're interested in the ultraviolet properties is not because, okay, we're going to do this and then all of a sudden we have a reasonable theory of quantum gravity. But if the theory is finite, it's for a reason. There's a symmetry there. And personally, I believe there's no way in hell you can have something like that happen, and it's not relevant for nature. There's some important symmetry that we're after. Now, let's suppose that the theory is finite. There's a lot more work that you'd have to do before you could declare, oh, I have a reasonable theory of quantum gravity. There's non-perturbative issues. There's high-energy behavior. Also realistic models. This thing it doesn't have chiral fermions, for example. But anyway, this is the first question I think it's an important question that needs to be asked about quantum gravity. Is it true? So let's see what people said about this. So this is just some amusement. This is from the 80s. And this is when supergravity was the biggest deal in town. People were extremely interested in supergravity because they were hoping it might be finite, yeah?
So I'm just wondering how much of what we're going to be saying applies to Einstein gravity?
A lot will apply, but not the finiteness. That theory is most definitely not finite. And the reason is because someone did a calculation. So we just absolutely know what the answer is. It diverges at 2 loops. Right? But, well, yeah. You need some supersymmetry. Okay, there's something going on in gravity, but you need some supersymmetry to help you to make the theory finite. So it's not just supersymmetry alone. And if you take away the supersymmetry, it's not going to work. Okay, so it's some combination of supersymmetry and something else. Okay, so what did people say in the 80s? In the 80s, this is a very typical quote from this is Howe and Stell. Unfortunately, in the absence of further mechanisms for cancellation, the analogous n equals 8, d equals 4 supergravity theory would seem set to diverge at 3-loop order. And notice actually how cautious these people are. They don't say, oh, look, it's going to diverge. That's people who quote these people say that. But the original people were much more cautious because they, of course, would only say what they knew to be true. Actually, here's a very nice quote. They also said 3 loops. But anyway, the final word on these issues may have to await further explicit calculations. It's my kind of guys, right? You know, it's like no fooling around. We got to do some calculation and understand what's true and what's not true, and you know, enough of this arguing. Okay, and this was the counter term that people expected. It's an art of the 4th counter term, so that's 4 gravitons. By art of the 4th, I mean the square of what's called the Bell-Robinson tensor, but I'm just going to write it schematically. Okay, and the 1 over epsilon is the ultraviolet divergence. Okay, so you can go around the room and ask the professors, what are the odds that the theory is finite? Well, I'll just throw some words in their mouth. They're going to say something, oh, that's completely crazy. These people are wasting their time. And maybe people who are a little more thoughtful might say, well, you know, maybe it's interesting, but it can't be finite. And actually, don't ask Nima. He doesn't count, because he might actually say something positive. And if he says that, then it's going to ruin what I'm saying. So don't ask him. Anyway, so let me ask you, how are you supposed to argue with a room full of experts and a Nobel laureate who I see isn't here? Okay, students who think you're crazy. Oh, no, it can't be finite. That's just crazy. Well, of course I think it's finite. Do I think it's finite? I think it's finite. So how am I supposed to argue with them? Well, if you've been to David Gross's lecture, you know the answer.
He's crazy.
Yeah, right. Anyway, so David Gross gave the answer. What you got to do is you just shut up and calculate. You know, it's in enough debates. But I've got some warnings for you if you think, hey, this seems pretty cool. I should do some crazy stuff. But first thing you should do before you embark on something like this, think long and hard. So actually, I thought about this problem for more than a year before doing anything. I was just thinking about it. Might it be? Might it not be? So you have to actually think about it a lot, because there's a reason why the experts are experts, right? And then something else very important before you do anything like this. Think about what else you can discover along the way, right? If you're going after something that's highly non-trivial, would take a lot of work, make sure that it's a good path. Along the path, good things happen. And then, this is the most important one, right? Have some tenure. Okay. But anyway, what we're going to do here is talk about how these ideas, they're going to help us answer this question. So we're definitely going to have the answer. But let me just amuse you. Suppose you were to go ahead and say, well, this newfangled stuff, I don't believe it. Let's just do it the honest way. We use Feynman diagrams. So you're welcome to go do a little bit of arithmetic and just do some counting of how many terms there are, the number of terms in the propagator, the vertices, and you get these completely ridiculous numbers, like 10 to the 20th at 3 loops, 4 loops, 10 to the 26 terms, 5 loops, 10 to the 31. By the way, that's more terms in the expression than a graduate student has in his brain, his or her brain. Therefore, the graduate student can't do the calculation. Anyway, you can count this. If you don't like the way I counted it, you're welcome to count it any way you want. The answer is this is never going to be done, not with Feynman diagrams. But let's recount. And this count I'll show you because I'll just do the calculation. So we're going to do 3 loops on the blackboard. The problem gets reduced to working out basically 10 terms. It's not Feynman diagrams. By 4 loops, okay, we're talking about 100. You do that on a computer in no time at all. It's a few minutes of calculation once you've set it up. And then 5 loops, okay, this is more complicated. We're talking about 1,000. There's about 1,000 of these types of diagrams, so there's about 1,000,000 terms. Okay, so that's more complicated, but 1,000,000 we can do on the computer. Anyway, supergravity is back. So it's pretty clear there's something going on here, but the finiteness is still not clear. So just to just list some people and just make some comments about what's been done. I don't want to use up too much time because I got to finish the 3-loop calculation. But anyway, the first thing is we have unitarity method. You could calculate all these on-shell techniques. We have now the double copy, which we discovered along the way of doing the calculations. It's related to something at tree level called Kawhi-Leland-Tie relations. There's string dualities. That's something pioneered by Michael Green as a way of getting a handle on the ultraviolet divergences in field theory. There's something called pure spinors. This is from Berkovitz. It's imported from string theory, but now used in field theory. Again, Michael Green and his collaborators. And then better understanding of symmetries. There's a symmetry, a well-known symmetry. It's called E77 of n equals 8 supergravity. Actually, first, Nima and his friends pointed out the importance of this, that it constrains the S matrix. Anyway, lots of people have now written about E77, and there's a lot understood about it. And I'll make a comment in just a few minutes about it. OK, let's see what happens if you calculate. So this was done without the double copy because we didn't know about it back then. But we had unitarity, so we just did it. Anyway, the answer, what people said in the 80s is just not true. There is no 3-loop divergence. And we know for sure because we did the calculation. It's very finite, in fact. Right? For d less than 6, it's finite. Not just in d equals 4, not just in 4 dimensions. OK, so what happens? You do a 3-loop calculation. You can just guess immediately what happens. Some people will say, oh, I said this before. Other people will say, oh, yes, very nice. But trouble is going to happen at 4 loops. Well, OK, my friend Kelly Stell wrote a paper. He said, maximal supergravity is likely to diverge at 4 loops in d equals 5, and then at 5 loops in d equals 4. I can tell you, make a statement like that near me, you better put up a bottle of wine. That's an Italian Barolo. That's actually the real bottle of wine. So, OK, once there's a bottle of wine at stake, OK, then I'm going to calculate. All right, so this is with my students. There's John Joseph Carrasco, Henrik Johansson, former students, I should say. Then Lance Dixon and Radu Roiban. And we just sat down and did the calculation, although it took us quite a while to do this. There's about 50 of these guys. There's planar, there's non-planar. By the way, the color factor of this guy is 0. It's kind of amusing. But anyway, but anyway, in n equals 8 supergravity, when you do this, it's the same set of diagrams, and you find that it's ultraviolet finite for d less than 11 halves. That's more than 5, bottle of wine. OK? Now, in fact, the way we discovered all this stuff about the duality between color and kinematics and the double copy and all of that, it comes from doing this calculation. So using this information, that we know there's now the double copy, and we know that now there's this duality between color and kinematics, instead of a year, it's actually quite simple to do the calculation. If you have used tools of Mathematica for keeping track of graphs, it's really just a couple days of work. Okay, what's the current status? Well, the status is, needless to say, if you show 4 loops is okay, needless to say, people will say, oh, that's very nice, but guess what's going to happen to you? 5 loops, there's going to be trouble. And in fact, they say that by 7 loops, there's going to be a valid ultraviolet counter term under all the known symmetries. Notice they don't say that anything about the unknown symmetries, but no surprise, they're unknown. Anyway, so I would say most reasonable people would say, okay, very nice, but it's going to all blow up in your face by 5 loops. Well, okay, you make a statement like that near me, you know what's going to happen. There's going to be some bottles of wine. So anyway, we're going to do the calculation, or we're doing it. We're actually very far along now. I think it shouldn't be too long now. Anyway, you can place your bets. So here's the specific bet. It's a specific technical bet at 5 loops. So 7 is out of reach. That would be the right calculation to do, but 5 is pretty good. So the bet is that in d equals 24/5, don't worry about fractional dimensions, we're theorists. Does n equals 8 supergravity diverge? So Kelly, him being from Imperial College, he put up a British bottle of wine. Me being from California, I put up a California bottle of wine. And Kelly says it will diverge, and I say it won't diverge. Okay, now, what we agree on, at least as far as I'm concerned, is if it diverges, if Kelly wins and I get this British bottle of wine, then I would say it's just game over. It's not gonna work anymore. So this really is the decisive calculation. If, in fact, it's finite, well, I think Kelly will probably buy a French bottle of wine, but I don't know. But also, he's going to do a backflip because he's going to be so excited that something wonderful is happening.
But still the 7 loops.
No, yeah, that's right. So the point is that, you see, if you ask me, why are you doing a calculation? Shouldn't you actually be trying to prove something? You know, do the proof to all loops all in one go? Isn't that really what you want to do? Well, the answer why we can't do that proof is because there's a problem at 5 loops that we don't understand. I'm quite confident that once we punch through this problem, then we're going to go on. Well, certainly the way forward, you know, the blockage is cleared. Okay? It's because that's the number. That number is, or 26/5 is the dimension in which n equals 4 super Yang-Mills diverges. This is a little bit worse. So it's really a bet about whether the power counting of n equals 8 supergravity is identical to that of n equals 4 super Yang-Mills. Well, maybe I'll have to explain that afterwards. I mean, where this counting comes from, I mean, I can't explain it. And oh no, this is very special. It's something very, yeah. This is something very special. It has to do with the relationship to n equals 4 super Yang-Mills. N equals 4 super Yang-Mills, like I say, it has a divergence in 26/5. If this guy happens earlier, then I would say game over. Okay. Yeah, it's game over. It's game over. Yeah.
You just say a few words about how things up to 4 loops, how that's at least morally related to the much better behavior of the trees or no triangles, one loop and so on.
Well. Yes, well, no, unfortunately, I think I'm going to have to say no. I don't, and the reason is because if I'm looking at the clock, I have exactly 1 hour now to do on the blackboard, and 3-loop computation on the blackboard. So you wouldn't want to ruin that. So. Okay. So anyway, now we should actually do the 3-loop computation on the blackboard and then get the power counting. And I'm going to show you there's no divergence at 3 loops. Okay. So first, Okay. Yes? What's that? There's a symmetry. Then we're going to build lots of models that have this property. I believe, personally, I believe one can build models of gravity that are self-consistent without strings. I'm glad David isn't here. Yeah. Anyway, I mean that's what I believe, but you know that I don't want to push that because you know it's a long way to go. Right now, it's just like I said in the beginning, it's just a question about symmetry, right? We just want to understand the symmetry of gravity. What's that?
If you are convinced, if I is convinced that it is finite, you should better start to think what's important.
No. That's because no one will believe me if I say it's finite. I need the calculation. Right? No one's going to believe it. I can say it all I want, but no one will believe. Okay, so I showed you these duality relations. So this would be a relationship. These are the diagrams that are non-vanishing. So that first one is a relationship between diagram, not the first one, but this thing here, between diagram D is related to diagram B, related to diagram H. So where's my diagram D? It's this one. So you see right around here, I have a 4-point guide marked by this. So I do the Jacobi relation on that. And that Jacobi relation is exactly this. And then I want you to notice the arguments, that you have to keep careful track of the arguments, the labels of loop momentum. Right? So on the left-hand side, the labelings are 1, 2, 3, and then there's L5, L6, L7. Those are the independent loop momenta. That's on one side. And it says it's equal to numerators with specific labelings. Right? So you have to keep track of these labelings because the integrand has certain labels on which loop momentum you're talking about. Okay, that's the first point. So it's actually a fairly straightforward exercise of just going through. You pick a certain leg. You do a Jacobi around it. That Jacobi. Actually, let me actually not circle this one. Let me circle down here, and then we circle. Well, the red circles mean something else, which I'll show you in a second. So this would be an example of a Jacobi relation. So it's just a graphical manipulation along the lines of what Nima was saying. There's some graphical manipulation, but it represents exactly one of these equations. Now, one of the tricks for doing, let's say, n equals 8 supergravity on the blackboard is I have to use some special properties of the n equals 8 theory. And that's allowed because by definition, if I'm doing 3 loops, I know everything about 1 loop. Right? And in fact, this is very well known to people in the field. So if we're doing, let's say, 1 loop, which I hope you can actually see, then there's a very simple rule about n equals 4 superioring nils. And that is that a diagram like that has the bubble in it, it's not there. And that's actually connected to the finiteness of n equals 4 superioring nils. There's no vacuum polarization. And then other examples, there's also no triangles. So let's say a diagram like this, that's also forbidden. Okay, so there's no triangle subdiagrams, no bubble subdiagrams. Let's look over here, the consequences. Look down the list. Do you see a 1-loop triangle or a 1-loop bubble? No, because they don't belong. And remember, we can think about things on shell. I isolate any 1-loop subdiagram, and I look at it, and I better not have one of these 1-loop subdiagrams, like a 1-loop guy sitting there with a bubble or a triangle. That's why it's not present. Now let me show you how you use that in the Jacobi relation. Notice this diagram here. Is that diagram in the list? Do I see it down there? No, I don't see it there. Why is it not there? Because I'm going to do the Jacobi identity on this leg here. That Jacobi identity for the numerator says this guy is equal to this guy minus that guy. What do I notice about this guy? Right there, one loop triangle subdiagram. So this guy is 0. I look over here. What do I notice about this guy right here? 0, because one loop triangle. So therefore, that diagram is 0. And it also explains what happened here. Like I have NA equals ND, and the third guy is missing, and that's because the third guy had a triangle subdiagram in him, so he got wiped out. Okay, so that's an example of one loop information we can use. More one loop information that we will use is if you're looking at one loop, then this guy, the boxes, so have no powers of loop momentum of L. There's L. L in the numerator. So I'm just quoting well-known things from n equals 4 super Yang-Mills amplitudes. And then the pentagon, another observation is that the pentagon, for example, here we have a pentagon subdiagram. You see the pentagon subdiagram, the one loop subdiagram? This guy should be linear in the loop momentum. Okay, these are just well-known facts, and I'm going to use them. Now, another thing I'm going to use is dual conformal invariants and the fact that we know everything about planar. In fact, we've known these things well before dual conformal invariants, but basically planar is a solved problem as far as the integrands are concerned. Notice the planar diagrams here, here, and then it was this one. So the well-known answer that you look up from the literature, and I assume you're going to allow me to define planar is very easy. I think from Nima's lecture we can deduce it is very easy, especially once he talks about dual conformal invariants. So I'm just going to use planar. So roughly speaking, you're never going to look at non-planar unless you know everything about planar. I mean, that's so we can accept that we know everything about planar. So I just looked this up. Actually, this is from a paper from the 96, I think, a long time ago. But anyway, my students wrote this down. This guy, the numerator, sorry, it's so unbelievably unreadable. Where's the, I need the eraser. Oh, yes? Did someone say something? I got a better solution. Okay, so we looked this guy up. Ah, that's a much better solution. Even I can see it. Okay, S cubed T a tree. This is the numerator. Remember, S is the Mandelstam invariant. Oh, very good, thank you. Now I can see it. Okay, K1 plus K2 square, and T is K2 plus K3 square. And we could put some labels on here, 1, 2, 3, 4. Notice this guy is independent of loop momentum by that rule that you couldn't have gotten any loop momentum. It would violate the no powers of loop momentum rule. Then second diagram, this guy, what he is S square T a tree, and then let's put L here. We'll put L5, and then 1, 2, 3, 4. So this is K4 plus L5 squared. And this is times. Okay? And then there's the last diagram, or potential diagram. There's a guy that looks like this. I'm writing him the other way, I think. But anyways, this guy, this is just 0. And this is the known answer. Now, you may notice that this guy seems to violate the pentagon rule. You see there's the pentagon? There's like an L square. But don't worry about that, because an L square, what he can do is he can cancel a propagator, and then he's down to this case. Right, so these guys actually mix, and then in this case, there'd be no powers of loop momentum. So I'm not actually violating the rule. Okay. Anyway, this is well known for many years. So anything that's well known, we define as I'm allowed to use it. Okay. Now, what's an important property that this thing has? Well, Nima was talking about leading singularities, and he was talking about building these types of diagrams, not to be confused with those diagrams, but diagrams built out of amplitudes, like so, where everything is on shell. Okay, so what's an important rule is if I take the known result and I put all these intermediate guys on shell, I have to get the right maximal cut, or the right, by maximal cut or leading singularity, I mean just put all these intermediate guys on shell. If I didn't get the right answer, then this thing would be wrong. So obviously I get the right answer, since that's the right, this is right. So there's a very simple rule now. Right? What I want to do is modify this so that all the duality equations hold. If you check it and you take this and you plug it in the duality equations, you will find it's inconsistent. That basically you're going to start at diagram E, you're going to do Jacobis, you're going to wander around, and then somewhere you're going to get back to diagram E, and it's going to be inconsistent. But see, the point is, this is not a unique answer. It's just a representation. We can push stuff between here and here, for example. Right? See, there's like a squared propagator, or inverse, which might cancel this guy here, and then it mixes with that guy. So I need to push stuff around. Right? But I'm not allowed to push stuff around in a way that I change the maximal cut. So then I immediately get an idea, oh, what I should do is take this guy and add stuff to it, but add stuff which does not change the maximal cut. So it doesn't change this picture that Nima was talking about. So what can I write down? I'll just add stuff like alpha s plus beta t, and then L5 square. That's one possibility. See, L5 square, it vanishes if I put these legs on shell. Right? So of course I can add it without changing the maximal cut. And alpha and beta are some parameters which we will figure out. And then you say, but wait, there's other places you can add stuff. For example, right here, I can add something. So let me add something. So let me add gamma s plus delta t. And then L5 minus K1 square. So the first thing I added would cancel this propagator, the second one this one, and then obviously I can add something more. Now, that thing that I add, notice that I have a symmetry in the diagram, right? If I flip the diagram over, it's the same diagram. So that tells me immediately whatever I add should respect that symmetry. So in fact, I'll do that. Same parameter, alpha s plus beta t, and then L5 minus K1 minus K2 square. And here I have 1, 2, 3, and 4. Now, can I add anything else? suppose I added some L square thing to this guy right here, then I violate the rule that a box subdiagram can't have any loop momentum. If I add it here, it again violates this box, then picks up loop momentum here, 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 here. I can't do anything. So that's it. Okay, and there's the secret of how I can do 3-loop supergravity on the blackboard. The ansatz, the manipulation of how to modify this diagram from a known result, only involves 4 parameters. Right? So now what we need to do is fix those 4 parameters. So the first thing you may notice is, in fact, I violated something I said. I said the pentagon, this here, this pentagon around here, this pentagon can at most be linear in loop momentum, but notice I made it quadratic. So let me get rid of the quadratic one. So that imposes constraints. I just pick up the L5 square from here, L5 square from here, L5 square from here, and that has to be 0. So I then immediately get constraints. So the coefficient of S, I would have 1 plus 2 alpha, I hope you can read that, plus gamma is equal to 0. There's the 1, there's 1 alpha, 2 alpha, plus gamma, that has to be 0. And that's eliminating the quadratic term, which is not allowed by knowing how one loop works. Then for the coefficient of t, there's t. Again, I get an equation. And the equation I get is t 2 beta plus delta, which looks highly unreadable, but OK, we're trying, is equal to 0. OK, so that tells me, if I solve those equations, I get that gamma is equal to minus 1 minus 2 alpha. So that's just right from here. And then this one says that delta is equal to minus 2 beta. So what I do is I take this, I plug it in here, right? And now just a little shaking. I'm going to skip trivial steps of algebra. OK, I'm going to transform this equation. So I'm going to erase it and replace it with it's nothing more than I take I just substitute. See, there's the delta. I just substitute in. There's the gamma. I just substitute in. I just shake it very slightly. And maybe just to help me along, let me define that the numerator, so nx is equal to sta3. Oh, actually, sorry, I had a little error that I had a little error. Sorry. I erased it so you can't see that I did it wrong. But anyway, there was a sta3 that I didn't put in the right spot. But anyway, just a little error. Okay, but anyway, let's just go on. So anyway, there's what I really want to do is just get rid of this factor. So I want to define the numerator not to have this factor, and that's a universal factor that I don't have to worry about. In fact, this thing has crossing symmetry. So you don't even have to worry about permutations, because there's going to be all sorts of permutations, and never mind that. That has crossing symmetry. So the equation I'm going to write down now will be for numerator, this is our diagram E. So the numerator E, remember that's our master that determines everybody. He's going to be equal to S, and then 1 plus 2 alpha minus beta. And then I'll define tau in just a second. Tau 1,5 minus tau 2,5. And then plus beta S, and then no, sorry. Sorry, I'm writing some, sorry, it's just a mistake. Anyway, so what you do is, the equation that I had before, you just plug in this, you just plug this in. Okay, and you get something very simple. Okay, so now we need some more information. So where are we going to get it? So the trick is, you just pick yourself a very convenient diagram to work with. And the guy I'm going to work with will be this guy, diagram J. So let's look at the equation, the Jacobi identity for diagram J. So where is diagram J? Well, let's mark him right here. So that's the Jacobi I'm going to use. So Nj is equal to Ne. So this is one of the equations I had before, but let me write it out. K3, and then L5, L6, and then L7. Okay, and there's some labeling here. Oh, there's L5, there's L6, and there's L7. And also in here, there's diagram E. Oh, I see I did it wrong. This is 5, and then 7, and then 6, like this. Sorry about that. It's completely unreadable. But the labels I want to match right here to be exactly the same in this diagram as in that diagram, the inner labels. Okay? So Nj, this would be one term in the Jacobi. The next term in the Jacobi, Ne, and then K2, K1, K3, L5, L6, and L7. So you notice the only thing that happened is legs 1 and 2 got swapped. So if I draw it pictorially, that Jacobi identity is the following. Is equal to this. 1, 2, 3, 4. 1, 2, 3, 4. And then minus, again, it's diagram E, except I do a permutation of the legs. Right? That's the twist. And then to draw where my Jacobi is acting, it's around here, it's around here, and then it's around here. Okay, and that's the 4-point subdiagram where the Jacobi identity is acting. And then all the labels, you notice the rest of the diagram, and all the labels, they're identical in all three. So there's no labeling confusion. And here you can see 1, 2, 2, 1. Okay, so now what I do, I have diagram E. I just worked it out. So now what I do is I plug it in with the arguments, call it canonical, 1, 2, 3, 5, 6, 7. And then I have to, it's a function, so I relabel 2 and 1. Okay, and I plug that in. And then I just do a little bit of algebra. So a little algebra, which I leave as a homework assignment. Since I got to squeeze it into an hour, I'm assigning just a little bit of homework. No. It will not. It will. This thing is neither anti-symmetric or symmetric. There'll be some piece that's anti-symmetric, some piece that's symmetric. Anyway, you do this, you get something. And let me show you what the something is. The something that you get. So this is after just a couple minutes of algebra. And if you're one of those impatient people, just type it into Mathematica and say simplify, right? You know, don't fool around. But anyway, you very quickly, just a little bit of algebra, you get the following result. And that's in terms of the parameters that are still left. It's S, 1 plus 2 alpha minus beta. Oh, and sorry. So let me define tau 15 is equal to 2k1 dot L5, or let's make it tau ij is equal to 2ki dot Lj, just to make it a little bit simpler to write. So L is a loop momentum, k is an external momentum. So let me just write this then as tau 15 minus tau 25, and then plus beta s, and then you get t minus u. So this guy here is antisymmetric, right? This piece here is antisymmetric, and this guy is neither. Now, you expect an antisymmetry, right? If I have legs 1 and 2, you expect an antisymmetry. So, in fact, you expect this to be a surviving term. Now, let's look at the top here. I said that this has loop momentum. Let's look at our diagram J. There's diagram J. What kind of subdiagrams do you see here? I see a box, I see a box, I see a box. How many powers of loop momentum can be in my answer, in the numerator? Right? The rule is none. Ah, this has loop momentum. What's that coefficient? 0. That's 0. Oh, that's pretty cool. I'm down now to 1 parameter. So I have now that beta is equal to 1 plus 2 alpha. One more parameter to go. Now, there's many ways you can get this parameter, because if we're on the right track, every single unitarity cut is supposed to work, right? So we can pick unitarity cuts, or that's one way to do it. You can look at various symmetry relations. This diagram has some funny symmetries in it, and you could use that or other ways. But what the heck? I only want to use planar information that's kind of obvious. Look at this guy, diagram A. Yes?
From the current presentation, it's not clear that we have the right number of equations.
That's correct. That's right. That's why this has to be checked. So there's no proof of what I'm saying, except in this case and a whole bunch of other cases, because we've done it. So a priori, you don't know if this is going to work. You might find it's inconsistent, for example. But OK, we're just going to proceed. Because if this is working, I can do 3-loop supergravity on the blackboard, right? OK, so let's look at diagram A. Because diagram A I like a lot. Because what do you know about diagram A? How many powers of loop momentum can I have in diagram A in that numerator? Box, box, box. 0. So in fact, we know the answer. The answer is exactly the same as the dual conformal answer. We know that diagram A So we know that diagram A, the answer has to be it just has to be S squared. I don't know if you can see that, S squared. And that's the STA tree removed. I give up. OK, let's go over here. I don't need this anymore, right? Because, OK, we got that beta is 1 plus 2 alpha. OK, so now this diagram here, right, his value is S squared. And that's drop the STA tree that's sitting out in front. Okay? So it's these capital N's I'm talking about, not the little ones that have the STA tree in them. So now what do I do? Well, if I had a better blackboard, I would have pointed to exactly which duality equations. But anyway, you can imagine there is a solution of diagram A in terms of diagram E. And let me just show you a couple terms. Yeah, we don't need this anymore. Let me just show you a couple terms, what it looks like. Because you see, we know the value of this diagram, right? So now what we have to do is make sure the duality equations give this result. So NA, if you plug in, this is straight from the duality, you'll get something like NE and then K1, K2, K4. And this has the canonical ordering, 1, 2, 3, 4, and then 5, 6, 7. And then minus, okay, let's put a comma here, comma, comma, minus K3 plus L5 minus L6 plus L7, and then L5 minus L6 minus L5. And then plus 5 other NEs. By the way, you can, this is going to be in a paper that's coming out hopefully in just a couple days. You know, the details of this that you can look up. The paper's on 4 loops, but we explained 3 loops. And this is basically out of the paper. So anyway, NA is now expressed in terms of the NEs. NE we know because we worked it out, and we have all but one parameter left in it. So you just take the NE, you plug it in there, you're careful with the labels, and then out on the other side you find that, so a little algebra. And you know, I'm not joking. This is just a little bit of algebra. You just do it on a piece of paper. It's nothing too significant. So a little bit of algebra, and what you find is NA is equal to S squared. Oh, that looks pretty good. Plus 1 plus 3 alpha. Alpha was the only parameter left in my problem. And then you get things like tau 1, 6, tau 4, 6, S minus 2, you know, etc. Now, let me look at this thing. Well, there's 2 ways I can tell that all of this stuff, which I'm not going to write down, but it looks basically the same, is 0. One way is I need this to match that, therefore this is 0. Another way I can tell that immediately is this carries powers of loop momentum. So it has to be 0. Now, the very fact that I'm finding a solution is already a very good sign. So in fact, that tells us that alpha is equal to minus 1/3. And that's it. We're done. OK, now, if you want now the complete amplitude, the duality equations tell you all the others. So if I know this guy now, then I can work out this guy, just following the duality equations. But not only the duality equations. You see these guys that I marked? Every single line has a Jacobi relation. Every single Jacobi relation has to work. If it does not work, I did it wrong. There's an inconsistency somewhere. So you have to then go home. So that's the homework assignment. Look up the result in our paper, and then march through every single Jacobi relation. And you get actually pretty good at it. You don't need a computer for this. And you make sure that they all work. OK, I can tell you the answer is they all work. In fact, let's just write down, just to admire it, what NE is. So let's put back little e. So now it's STA tree sitting out in front. And then we're going to put in S. And then it's tau 4, 5 plus tau 1, 5 plus 1/3. I mean, the 1/3, of course, snuck in because one of the parameters had a third in it. Plus 1/3 Whoops. I'm going to run out of space there. So then plus 1/3, and then t minus s, and then s plus tau 1/5 minus tau 2/5. And there he is. So this is the complete solution of the 3-loop amplitude in n equals 4 super Yang-Mills theory. To make sure that it's the complete solution, you have to work out all the unitarity cuts, which actually is a very easy problem if you already have another representation, because then you're just comparing the cuts of the known answer against these cuts, and you just march through it very quickly. Okay. So to state, well, I'll try on this board. I'll just stick to this board. Okay, so to state it, A, n equals 4 super Yang-Mills, 4.3 loop. Okay, I'll put in the coupling constant. Okay, what happened to the coupling constant? Okay, I'll put it in. You have to sum over the permutations. So the permutations of, there's permutations of external legs. So there's 4 factorial, but there's overcounts. So anyway, and then I have to put in some symmetry factors, but okay, that's not a big deal. But it's clear you have to sum over permutations. Like this could have been 1, 3, 1, 3, 2, 4, or something like that. So you have to sum over all those permutations. But all those permutations are just relabelings of this, because I maintained the symmetry. By the way, that's something else you have to check. If the answer doesn't have the right symmetries, then of the diagrams, like you work out this guy and it doesn't have the right symmetries, then there's a mistake. It's an inconsistency. Okay, but anyway, if you do that, you will find it's the right answer. Then we have to sum over all the diagrams. And there you have, it's the 12 diagrams that are sitting there. And then integral from j equals 5 to 8, dli, and this is d, and then 2 pi to the d, and some normalization. Okay, and then these are labels 5, 6, 7. Then we have our STA tree. Then we have our color factors. What's the color factor? Just stick FABCs here. Then we have these numerators. Well, yeah, we have the numerators. So it's just this part here. We have these numerators. And then we have the denominators. These are the Feynman propagators. Okay, what are the Feynman propagators? Just look at the diagrams. Okay, and this is the answer. Now, who can tell me how to do n equals 8 supergravity? What am I supposed to do? Yeah, right. So I cross that out. I don't like that. And then I square it. And then I change that. And I'm done. So that's n equals 8 supergravity. Now you might say, oh, wait a second. That's too fast. How do you know it's right? Unitarity cuts, right? You check that all the unitarity cuts, so what Nima was talking about, you check that all the unitarity cuts are right. Oh, this wasn't E. Sorry, this was like X, you know, or I. Let's make it J. J. So it's just these are just numerators. I shouldn't have said E. It's just the sum over all the diagrams. Okay, and the propagators of all the diagrams. Okay. Anyway, this is now the n equals 8 supergravity answer, and oh, yeah, there we go. Okay, we have to change the coupling constant. Now, notice that this thing carries dimensions. Right? There's some dimensions here. And that's, of course, oh, not squared. This is the 8th power. So notice that this thing carries dimensions. And of course, that's related to the fact that this carries dimensions. Okay, so now let's ask the next question. Now that we have this, and the thing I'm not showing you, but the assertion is that by checking the unitarity cuts we have it right, let's find out what dimension does the 3-loop expression for n equals 8 supergravity, what dimension does it diverge in? Right, let's find that out. Okay? So I walk through the guys with the worst power counting behavior. Diagram E, it's the master. That guy is the worst guy you're going to find. Also, this guy is, if you do the counting on him, he's also the worst guy. And we can actually see the counting. You square this, right? So that means 2 powers of loop momentum in this numerator. This guy, J, notice he's missing a propagator. So it's as if though you had 2 powers of loop momentum in the numerator. So this guy and this guy are in the same class, but we can count them. It's all on the same way. If you look through all of this stuff, you'll find that nothing has more than 2 powers of loop momentum in the numerator when all the propagators, the internal ones, are present. And all these guys that are missing a loop propagator, they have no powers of loop momentum. There's the rule about the box subdiagram. Okay. So we count. So this is now power counting. So in fact, I'm not proving that the bound is saturated. I'm just going to put a bound on it. So let's count. Well, how many loops do we have? We have D, D, L. Let's make it cubed because I have 3 loops. Right? Then how many propagators do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Anyway, it's 10. And then, so that gives me downstairs, I have L squared to the 10th. Upstairs in this diagram, as we just said, I have to square it, so I have 2 powers of loop momentum. So there's an L square up here. Okay, I do the little bit of arithmetic. I get that 3D is less than 18, makes this integral finite. So therefore, in D less than 6, it's finite. Now notice that 4 is less than 6. Therefore, it's finite in 4 dimensions, unlike what was said in the 80s. Now, next question you can ask. Yes?
When you vary the number of dimensions, you keep the number of supercharges.
Yeah. So the great thing about n equals 4 super Yang-Mills or n equals 8 supergravity is we get it by a dimensional compactification. So when you're playing games, moving the number of dimensions up and down, the states don't change on you. By the way, there is actually something important. So the starting points I used, so I used these planar guys starting points. By explicit computation, we know that these guys are valid in d dimensions. And then the duality just carries you to make all of the rest valid in d dimensions. Because that duality doesn't care about dimensions. I mean, there's some long story about dimensional regularization and so on, but okay. Now, you can have another question. Is the bound saturated? So, now, if the bound was not saturated, there'd be something very peculiar happening, that n equals 8 supergravity would be more finite than n equals 4 super Yang-Mills. That would be pretty weird. But anyway, we decided, there's only one way to find out if the bound is saturated. It's like David Gross said, just shut up and calculate. So we calculate. So now you have to actually do the integrals. There's an integral to do. But the integrals are not so bad because we're only interested in the ultraviolet divergence. And it's, in fact, the very first ultraviolet divergence of the theory, so there's no subdivergences. And you just sit down and you just do the you just do the integrals, the ultraviolet integrals in no time. And in fact, we know that by that we know what the bound is, that the bound is saturated. But in this case, there's really no, you can't have a symmetry argument. There is no way to know this without calculating. Because if you have a symmetry argument, to know whether this is saturated or not, the problem is what happens if you miss a symmetry? It's like lack of knowledge. If there's some lack of knowledge and there's something going on that you don't know about, the only way you can find it and be sure that you didn't miss anything is you just do the calculation of the ultraviolet properties in d equals 6, and then the answer is the thing diverges. Now, if you do for loops, everything I said carries through. It just works immediately. No grief, no mess. Instead of an ansatz that has 4 parameters, okay, it's a little more complicated. You get, actually the number turns out 86 parameters or less. But it depends how you do it. But anyway, once you're on a roll and you're doing these Jacobi identities, in minutes you just solve the system of equations. It's child's play with Mathematica. And the result by doing that is you get, again, manifest agreement between the power counting of n equals 4 super Yang-Mills and n equals 8 supergravity up to 4 loops. So let me just put it here. So the same story holds at 4 loops. And it's finite for d less than 11 halves. And we know the bound is saturated because we did it the old-fashioned when we actually did the integrals. So we know that bound is saturated. And that means up to 4 loops, n equals 8 supergravity and n equals 4 super Yang-Mills, which is a finite theory in 4 dimensions, they have exactly the same behavior. So as I alluded in the beginning, the question now is 5 loops. What's going on at 5 loops? By the way, I am very pleased with myself. If you check out the time, I did it in less than an hour. But anyway, so if you check out 5 loops, the question right now is what's going on at 5 loops. So there's one of the 5-loop guys. There's about 900 other guys like that. So it's a little bit more complicated. And the question is, once again, does n equals 8 supergravity have the same degree of divergence as n equals 4 super Yang-Mills or not? And the specific bet, or the specific question is it finite for d less, I don't know if you can read that, but d less than 24 over 5, or d less than, or d less than 26 over 5. This number here, that's the degree of divergence as n equals 4 super Yang-Mills, same as n equals 4 super Yang-Mills. Okay, and that's. What is the 24? Oh, this is basically, if it's worse, then what happens is, well, if you add 1 more power of loop momentum, it doesn't count because then you get an odd number and the thing integrates to 0. So you have to add 2 more powers of loop momentum to have a difference. So that's why this number shifted by 2. Okay, well, that's it. Anyway, we're going to do the calculation. We're most of the way through. And I hope to have the answer soon. Okay, thanks. Questions? Yeah. Yes. Well, I'm not actually sure that it's a symmetry, but one thing for sure, it's actually connected to what Nima was asking. It's very, it's connected with the large Z behavior of gravity. So you see, if I take, let's say some tree amplitude, and let me just draw like a Feynman diagram. And then Nima was talking about shifts. Okay, I'm going to shift momenta. Nima would shift spinors, but okay, shifting momenta, shifting spinors is the same. Let's just shift momentum. K goes to K plus Z times something. And never mind, I just want the behavior Z times something else. Let's call it Q, right? And let's look at gravity, right? So gravity, by its power counting, has 2 powers of momentum at each vertex. So we'll put a Z square here, a Z square here, a Z square here, a Z square here, and et cetera. The more legs I have, things are going to get worse and worse. These propagators, they actually they have a behavior that goes like 1 over Z square because one of the conditions in the shift is that Q square is equal to 0. So in the propagator, it only behaves like 1 over Z, and then very quickly you decide, oh, that's going to blow up on you. That's going to have very terrible behavior as Z gets very large. But in fact, that's just not true. If you look at gravity, at the large Z, the shifts, and notice how the shifts are counting powers of loop momentum, right? If you do the shift, the true behavior is A of Z goes like 1 over Z squared. In fact, it's better than Yang-Mills. This, I believe, is, you could say, one way of understanding how there can be fantastic cancellations. Now, when you're looking at loop level, it's a little bit more complicated because you see there's just many loops and many momenta and many integrals that you have to keep track of. But you see, if you look at any subintegral and any kind of even subdiagram, like a tree subdiagram, and you look at how it's behaving, if you understand it properly, it actually behaves very well. But this, unfortunately, is not a proof because you have to show simultaneously that all the pieces simultaneously, no matter how you look at it, I look at this subdiagram or that subdiagram, simultaneously that it has very good behavior in the ultraviolet, just like the tree does, if appropriately understood. But it's this, I think, is one way to understand what's going on. Actually, Nima, I think it was Nima's first paper in the subject, actually discusses this.
And this factor, tree level, is associated with the symmetry.
Yeah.
Enhanced symmetry at infinite level, which you don't see at any point. Well, I don't know what its name is. We call it spin Lorentz.
Yeah, something like enhanced Lorentz symmetry. This is just tree level. Right.
E6.
Oh, you mean E77? Oh, right. So E77 is in fact the symmetry that's been used now to wipe out all the counter terms up to 7 points. But there is a complete consensus. Well, let me change that. There is nearly a complete consensus that that symmetry is not powerful enough to go on beyond 7 loops.
But how does
That has
that?
nothing to do with this.
Yeah, nothing.
See, that's
Yeah.
the property of pure gravity.
Right.
Even pure gravity, that's what's
Right.
interesting here. There's something mysterious even in pure gravity.
I'm not.
Yeah.
That's a tree, but E77 is a full thing.
Right.
How does it reflect itself in these lower order diagrams? Do you understand?
Well, yeah, and so again, I'll point to Nima. So there's some soft theorems about what happens if you take scalar legs soft, or there's double soft limits, and there's an algebra that goes with that. And in fact, that's what was used to restrict counter terms. So, yeah.
You're just
You mean related to this? Oh, no. That in fact, for a long time, I would make pronouncements that, oh, AE77, that's never going to be, what we're looking for. And that was related to the fact that this statement here about how gravity is behaving is for pure gravity. So the point is that I am pretty sure,
a tree, you can't.
right, but if you look at, let's say, one loop in which we analyze, you use this information of trees, you have the unitarity method, analyze what's going on at one loop, you will find fantastic cancellations and pure Einstein gravity at one loop coming directly from here, and that we tracked through. Unfortunately, we couldn't go on to higher loops because we don't have as powerful a formalism at higher loops as we have at one loop. You know, one loop, basically, we understand everything.
Let me ask
So,
a question.
yeah, yeah.
E7,
Yeah.
symmetry should have some implications for the graphical analysis.
Yes. Well,
Since it, as you say,
there is a, yeah, right, there is a little problem. If you look at individual graphs of this type, like this fellow, not this fellow, let me find another guy. Let me add some more loops. This fellow, if you try to do a graphical analysis and say, okay, I'll use E7, 7, 7, but it doesn't matter. This diagram here has bad behavior up at 7 loops. He will diverge. That one diagram. So the problem is that E7, 7, if you attack individual diagrams, it won't help you. And we know that for a fact because you cannot violate unitarity. The maximal cut of this thing is badly behaved. However, this does not necessarily mean anything because if there's anything I learned in this game, you should not look at individual pieces. This is one piece. You can start looking at non-planars. There is a very strong cancellation between non-planar and planar that we know about. So until we have the complete expression.
I understand. Well, let me
Yeah,
it's like
yeah, okay.
when I employ a symmetry to discuss renormalizability,
Yeah,
I'm not looking at individual diagrams. I'm looking at
Yeah.
the effective action. It sums over all the time. Now, you're discussing methods which sum over all the diagrams.
Mhm.
That's where the cancellations are going. I'm just, you think
Yeah.
at least up to 7 loops.
yeah.
That there should be some.
As far as I can tell and anybody else can tell, E7, 7 will not carry you beyond, you know, in any way.
And this might not carry you beyond either. Even 5 loops.
Well, we're going to find, that's why we're doing the calculation, because we're going to find out the answer. I mean, we can hold a debate and I can start talking about, you know, these various unitarity cuts and look at,
My
but,
question wasn't that.
yeah.
It wasn't, you know, where is it going? Where is it going to finally
Yeah.
be non-finite, or is it?
yeah,
It's just to the level you've worked.
yeah,
Both ways of analyzing
absolutely.
give
The same,
surprising results. Some
right,
character
that's right,
appears.
that's right.
So there therefore should be some way of relating those two ways of arriving at the same result.
Well, the situation is even worse than that because there are, in fact, multiple people who have different ways. And for example, Michael Green, he does it from pure spinors, and he has his arguments from using the pure spinors, and there is no E7, 7 in there, and he winds up at 7 loops. And you can, well, I think what's going on here is if you have multiple correct formalisms, and you're attacking the truth, so, you know, there's multiple formalisms coming at the problem from different angles, and then you're arriving at the truth, which is that there's no divergence up to 7 loops. But personally, I don't think E7, 7 is what we're looking for, or that it really has any.
If you want finite.
Yeah, for finiteness. But at least it's true. It's certainly true that all the, like the for loop result that we have, that can be explained by E7, 7, and all the way to 7 loops. What we can see in the unitarity cuts can all be explained by that. Sorry, at least these individual pieces. Now, the unitarity cuts are more powerful in the sense that they can grab for you collections of things. So if you look at a cut that goes down here, like down the middle, then you are, in fact, summing lots of diagrams, lots of permutations, and it's in that case that we see cancellations. And in that case, we know that the cancellations go to all loop orders. And it's, in fact, that specific fact, which is why I think it's going to be finite. But like I say, this year we're going to find out. You know, 5 loops, I think, will tell us, you know, whether I should be quiet and say, okay, done, you know, I'm not going on, or or whether we go on.
Just a comment about
Yeah.
E77 though. I think what people have been using so far is just the very, very simplest first implication of what E7 is.
Yeah.
E7R, which is the analog of the old
Right, right.
zero, right? I think they haven't even, I could be wrong, but the last time I checked, they haven't even been using the actual E7.
Yeah, you mean the algebra. That is correct. They have not been using that. Yeah,
And it could well
that's
be
right.
that if you look at enough of them,
Yeah, maybe.
strength coming from
Maybe. But you know, the thing is, the cancellations that you see at tree level and then at one loop, they don't have anything to do with E77. So to me, it doesn't seem that that's the crucial fact. But it doesn't mean that that's not a good way to look at it, because it's a very powerful symmetry. And if it's a true symmetry, you exploit it as much as you can.
No, but at one loop you don't need E7.
No, there you don't need it. But but I'm saying that at one loop in pure Einstein gravity, we see fantastic cancellations, which clearly have nothing to do with E77, right? Because you know there is no E77 in Einstein gravity.
Can I make just
Yeah.
a small comment about
Yeah.
E7? The on-shell understanding of E77 is, as we're saying, some property of the amplitude is scale and momentum versus. We already know that there's nice properties in pure gravity, important properties, just the soft limits for what amplitudes probably have to be gauge as graviton moments to go to zero. And I think that actually E77 is just the supersymmetric cousin of the famous old Weinberg soft limits. It's just that, so I don't think it's really on a particularly conceptually different footing than the ordinary soft limits. It just so happens that the old soft limits involve divergences in the amplitudes, and when you have scalar momentum going to zero, they don't quite show up as divergences, so you can see them as some action in, you can see them at the level of the Lagrange more easily. But the reason I say that is that is the fact that the graviton amplitudes have the correct soft limits, the fact that all of these things are even at tree level are very strongly related to each other and very strongly related to this remarkable behavior at infinity. So it could be that E77 is, if it's property thought of as a cousin of these graviton soft limits, it comes along for the ride with
Yeah.
supersymmetry, but it's really.
I mean, that could be an explanation of why E77 is addressing this question, even though a priori it didn't look that way to me.
So that's
Right.
what I want to say.
Right, that's a very good point. Right.
Super
Right.
partner of
Right.
this fact.
Right. Okay. Okay.